Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's really a great pleasure and honor to be able to talk about my work here. I'm going to talk about primarily about my thesis work, stacked graphical learning for text mining. And here's an outline of what I'm going to talk about. I will briefly overview what I have done in the past 7 years approximately, and then focusing on stacked graphical learning, the algorithms and the application so far, and a very recent online version of these algorithms, which is efficient in both training and inference. And if time allows, I will briefly talk about the recent project regarding to Netflix datasets. This is actually the work which stimulated my passion in working on applying learning models to solve real problems, to have impact on something closely related to people's life. Okay, so here is a brief overview of my research experience. This is back to the year of 2000. I was pursuing a master's degree at Tsinghua University. At that time, my work was mostly about image analysis. The first project I worked on is about classifying DNA images. So it's a multi-class classification problem. At that time, I applied support vector machines to do the classification job. And also I explored a little bit about a variation of support vector machine, which is called class mean SVM, something like that. Another project I did in Tsinghua is finding the feature point in facial images. And I applied the linear regression model to find the correlation between like the pixel values and the locations of the feature points. And we can clearly see those two projects involved a lot of learning models, and that's why I became very interested in pursuing a PhD at SMU. Then I applied and I got admitted. Very lucky. This is the first project I worked on at SMU. It's called SLEEF, basically a biological literature mining system. In this system, we analyze both the figures and text in biological papers, since in that domain, usually the figures carry a lot of information. One sub-project I worked on is related to OCR, but slightly different. Is now the task is to find the characters printed in the figure and to recognize this character. So it's both about text region detection and OCR. And another project within this SLEEF project is name entity extraction. That is to find the protein names in the text part. So you can see that from that project on, I kind of moved to the text mining part. At that time, we developed a model we call dictionary hidden Markov models, which can implement a soft match from a name appearing in the text to entries in the dictionary. And I also did some fun projects within the SLEEF, like I helped set up a database to store the information extracted and implement a web UI for external users to explore our information extraction system. So that's about SLEEF project. Then I kind of focused on my thesis and worked on stacked graphical models. I worked both on the theory part, like study why these algorithms would converge, and also explore applications in, say, document classification and also information extraction. And one thing I like to mention here is very great to find out that stacked graphical learning can be applied to learn subtasks in an information extraction system. For example, in SLEEF, we want to find the, say, protein names from the text, and also we want to match the information from the text into the image. So that's basically a matching from the information extraction job to the OCR job. So we're very luckily my thesis also provides a bridge to all my previous work. So this is just a recent project about link prediction, and the dataset is a Netflix training dataset. And the task was about recommending movies for users, particularly is to predict the probability of a given user reviewing a given movie. And this project brought up many interesting thoughts to me, like in this problem, I need to consider how to combine the features from multiple domains. And also I need to design a robust learning system since it's quite noisy, the real data set. And also it's a huge data set, we need to think about the large scale issues, either downsampling the training set or scaling up our learning model. So this is pretty much my experience from the year of 2000, and I feel really lucky to be able to work in this domain. Since from each project, I obtained some experience and some insight, and I really had a lot of fun working on this problem instead of just, well, it's something I was funded by. So now I decided to pursue a career in applying machine learning to solve real problems. And so from now on, I'll move to introducing the stacked graphical models. And this is an example of a relational dataset and the motivation for developing a stacked graphical model. For example, in the relational dataset, we can represent the dataset with a graph. Here, each node denotes an example, and each link corresponds to a dependency among the dataset. We can imagine this as a collection of paper with, say, co-citation relationship and citation relationship among them. Usually, there is one attribute associated with the nodes indicating the categories. For example, in this problem here, we might be interested in classifying the papers into various about artificial intelligence, about database, or about HCI, different topics. And if we look at the links, usually there might be different types of links or even attributes associated with links. For example, here we might consider citation and also co-citation. Here is another example. It's specifically for the WebKB dataset, which contains collection of web pages from 4 departments. And the links would be hyperlinks. In this problem, we might be interested in classifying the web pages into web page of a faculty, of a student, of a course or of a research project. And I would conclude in this kind of relational data set, we need to both look at the attribute associated with every example and also look at the dependencies among them. And this slide shows basically what we have looked at. So just some key features about a relational data set. We can view the nodes as objects, and in general, there might be several types of objects. Like in Netflix dataset, we can consider a type of movie node and another type of user node. And also the links might have attributes and might have different types. And another thing unique here is the number of neighbors is not fixed in general. That's how a relational data set differs from something can be modeled with say a Bayesian network. Since in reality there are many such relational data sets, and people are very interested in developing models to classify relational data. And those models are closely related to what I would refer to as collective inference. In those relational models, the class labels of all the related examples are predicted simultaneously. Instead of, say, the traditional learning algorithms like SVM or naive Bayesian, they treat the data as identical independently, say, IID data, and they ignore the dependencies among those data. So here I listed several example works in the relational learning domain. For example, people work on relational Markov networks, relational dependency networks, and recently Domingos provide a uniform framework called Markov logic networks. There's recently a book about relational learning. So we can see this is really an active research domain. And my thesis was not just about, okay, a new model to solve the problem. What we care here is the efficiency problem. Since most of the existing models are very original from graphical models, and the learning and inference are pretty expensive in the sense of it requires iterative inference. And also the learning procedure is an iterative optimization procedure that requires, in some sense, the inference, if we recall the learning procedure of a graphical model. So we want to develop a model that is efficient in training and testing, or at least in testing. And stacked graphical models are a procedure which can be very efficient in testing. And recently we developed the online version so that stacked graphical models would be efficient in both learning and training, which, well, I will demonstrate that later. So this is a big picture of the stacked graphical learnings. So this is a problem stacked graphical learning is trying to solve, to classify the relational data. And in stacked graphical model, we can break down the strategy into two steps. In the first stage, we predict the class labels primarily based on local information. Say we decode the relational data by ignoring the dependency among them. And of course, now we only have a very rough prediction, might not be that accurate. Then at the second stage, we extend the local features. Say we generate new features to include the information from all these neighbors. And usually, generating those new features would involve some procedure to find the neighbors and also summarize the information of those neighbors. And this is a big picture of the idea in stacked graphical learnings. And we can see within this setup, there are two issues we need to consider. First is how to get the predictions, and then it's how to generate the additional features to capture the dependency. So first, this is how we solve the prediction problem. This was from the original idea of stacked generalization. We apply a cross-validation-like technique to the whole training set. Say we split the training set into 3 disjoint subsets. And one thing I like to mention is, in general, splitting a relational dataset, you can imagine it involves graph partitioning or clustering. Since it's a relational dataset, the examples are linked to each other. You cannot just do random sampling. But empirically, we can apply some rules to split the dataset. For example, in the WebKB dataset, the web pages are from 4 departments. So a natural way to split the dataset is just by the source. We split them by department. And once we have those splitted dataset, we can train models for each subset and apply the corresponding model to get the prediction for that subset. And then we can generate new features to augment our local features. In general, generating new features is non-trivial. It involves a procedure to find all the neighbors, which is kind of natural. We can get that information from the dataset. And then we need to return the predictions. For example, in this WebKB dataset, given the web page W1, the relational template would find all the neighbors. Then the next question is how to generate new features. Here, it's closely related to the aggregations. And in my thesis, I didn't go further into the development of relational templates, but there are a bunch of existing logics to generate new features through aggregation. For example, we can get the count or average, that kind of statistics of the neighbors. In the WebKB dataset, for example, we apply the count aggregator, and the relational template might return additional features in this format, which means in the neighbors, there is 1 falling in the category 1, 2 neighbors falling to the category 2, and no neighbors in the category 3, 4, and 5. So that's about the general scheme for stacked graphical learning. And later on, I will refer it to as standard stacked graphical model. And we have applied this standard stacked graphical model into several domains. Here I demonstrate 2 domains, one in document classification and one in name entity extraction. In the document classification, we consider here 3 datasets. One is the WebKB dataset, which is to classify the collection of web pages. Cover dataset and CiteSeer dataset are 2 datasets of papers with co-citation relationship. And these datasets are of the scale of several thousand nodes. As I can remember, they are all about 4,000 nodes, and the links are about 8,000. And we compare to several models here. The baseline here is a classification built with max-end learning algorithms. And also this is the base learner within stacked graphical models, since the idea of stacked graphical learning is to augment the performance of a base learner by generating new features. We also use the max-end as the base learner in our stacked graphical learning. Another model here is relational dependency networks. It's one of the relational learning models out there. And in my thesis, I also presented the comparison to relational Markov networks. But for the slide here, I didn't include them just because of the concern of the times. The relational template here is the count aggregation. And another application is for information extraction. Here we consider extracting names from emails. That's some general name entity like person names and universities like that. And we also consider extracting protein names from some mainline abstracts. And here we compare our model to conditional random fields, and also a model called stacked sequential conditional random fields. And in this model, we only consider the dependency along the adjacent words, that is, along the sequence. And in the in the stacked graphical learning, the relational template design is much more flexible. We can look at dependency both along the sequence and also something similar to the skip chain CRFs. So for example, these are 2 identical words. We can add one more dependency among them. The table here shows the performance of stacked graphical learning applied to name extraction. And we can see, in general, compare stacked model to the conditional random field, there is improvement in the F1 accuracy. So it's almost, almost quite sure the stacking would improve the performance of the base learner. And compared to other stacked models, we can see since stacked graphical models can introduce more dependencies, like the long-range dependency among same words, it is better than just using the stacked sequential CRFs, which can only look at the dependency among adjacent words. And this model here is what we call ceiling for stacked graphical model. That is, when we're generating new features, we use the true labels for all those related examples instead of using the prediction. And this is kind of the best a stacked model can achieve. And we can observe that in some cases, like in the YAPAX dataset, stacked graphical model kind of do what it can do best. But in some cases, there's still room to improve the accuracy. I would say to improve a stacked graphical model, it relies on, say, a reasonable, well-based learner and also a nice relational template, since in this model we rely on the relational template to capture the dependency among those related instances. Here, I want to use the document classification dataset to show the efficiency of the stacked graphical learning. And we compare to the relational dependency networks by checking the number of iterations required to converge. We both compare the accuracy and efficiency, since it only makes sense to say there's a gain in speed up if they can achieve similar accuracies. And the plot here shows the efficiency on WebKB dataset. The red curve shows the performance of stacked graphical learning. And these two curves are obtained by GIF sampling with relational dependency networks. The blue curve here is a GIF sampling with random initials. And the black plot here is GIF sampling with the same initials as stacked graphical learning. Since sometimes you might argue, okay, stacked graphical model converge more quickly because it starts with a better initial state. And clearly, here we can see it's not the case. It's something related to the nature of stacked graphical model, which sort of guarantee the quick convergence of stacked graphical learning. And this slide here shows the performance on the Cora dataset and CiteSeer dataset. We can observe similar tendencies here. So stacked graphical models in general converge after 1 or 2 iterations. But GIF sampling, usually it converges after 100 iterations. Here is a table. It is another way to show the result. If we compare the accuracy from stacking to GIF sampling after 50 iterations, the number here shows the speed up. Say, in general, there's like 40 times speed up. But if we look at the accuracy, at this point, after 50 iterations, GIF sampling still hadn't converged yet. So the accuracy is kind of low compared to stacked graphical learning. And after 100 iterations, GIF sampling achieves a nice accuracy, but if you look at the time required to finish 100 iterations, it's over 80 times slower. So
Is it a speed up in number of iterations?
yes, it's in the number of iterations.
And is the comparable time for iteration?
I would say if we are going to look at the time, there are 2 concerns here. This GIF sampling also is like it has a local conditional probability distribution, and computing would involve going over all the data and also computing, say, one local probability distribution. Only if we set the local model to capture the local dependencies, if we set them at the same, it's kind of fair to compare the poor running time. And I did try that since I sort of implemented a naive version for relational dependency networks where I use a max-end learning model based on some relational features. Since in David Jensen's work, they propose to use that relational probability tree as say a standard model for the local relational CDF. So I tried to compare to their package, and I think it's unfair to compare since the local models are not the same. And then I did some work trying to prove that stacked graphical models can provide stable solutions, since where so far the algorithms is very heuristic. And if you look at the procedure of keep sampling and stacked graphical learning, we can formulate keep sampling as a homogeneous Markov chain, which means it has an initial state, and afterwards the parameters for updating the probability are the same. But in stacking, we start with some initial state, and we kind of learn new parameters based on the current performance. And in each stage, we have different parameters. So by taking more effort into learning this model and generating new parameters, we hope we can only rely on a few iterations to converge. So that is, the number of iterations here is much smaller than the number of iterations required in keep sampling. And the whole process here in stacked graphical learning is actually minimizing the KL divergence between some probability distribution we start with and the final true distribution we try to model. And I will show the outline of proving that convergence in the sense of KL divergence. Here is an idealized version of stacked graphical learning. If, say, we create the new dataset by generating new features based on those predictions y prime, and those y primes were drawn from the previous distribution, or it's the distribution in the previous iteration. And the parameters within this model would maximize the likelihood within the whole dataset. So this is the idealized version of stacked graphical learning. We should notice the difference here. Since idealized version, the y were drawn from the distribution from previous iteration, but in practice we kind of get those predictions in a cross-validation way, and then we use the relational template to pass on the information from those Markov blanket. But under the idealized version, we can see the procedure of stacked graphical learning is a greedy way to learn the parameters in the whole theory of Gibbs sampler distributions. So it's another way to learn those series of distributions. And we can claim that, in general, maximizing the likelihood is equivalent to minimizing the KL divergence. And that is actually the key point here. In the idealized version, as I showed in the previous slide, this is a greedy way to learn the parameters within that gives sampling distributions. And here, learning the parameters in a greedy way is just maximizing the likelihood. And then that's equivalent to minimizing the KL divergence. So ideally, those idealized version of stacking would converge as Gibbs sampling does. But in practice, since our algorithm relies on the relational template to return the Markov blanket, and also we rely on those cross-validation procedure to get the predictions instead of sample from the previous distribution. And at least that provides a rough idea showing why the stacked graphical learning would in some sense guarantee you achieve a stable solution. And so far we can see that stacked graphical models is expressive in the sense of it can capture the dependencies with the relational template. And if we look at the inference, it's very efficient compared to Gibbs sampling. But during learning, still there's a problem, since there's cross-validation involved in learning. In the sense of accuracy, I compared stacked graphical models to relational dependency networks and also relational Markov networks in my thesis work. And they are really competitive compared to the state-of-art relational learning models. So since the standard stacked graphical learning is expensive in learning the parameters, we consider to develop a model that is efficient in both learning and inference. And we can see the reason for expensive training is we have to rely on a cross-validation procedure to obtain the predictions for training example. Then if we think of a online learning algorithms as our base learner, in the online learning algorithms, usually we generate a prediction for the current training example, and we use this prediction to update our model. And so the first thought was, can we use this prediction, since we might think this prediction is not accurate enough. And we did figure out a way to compensate that. So the big picture is we can use the intermediate prediction in the online learning algorithm to generate new features. And also here we want a single pass online learning algorithm, since where we emphasize single pass online learning because if you think of voted perceptron, it still requires several passes over the training data and then average the model. Here we use a model developed by Viter in our group. It's called Modified Balanced Window, which is a very nice single-pass online learning algorithm and has been shown to achieve competitive results to other batch-level learning algorithms like SVM. This is a picture showing the idea of online stacked graphical learning. So for example, during the online learning procedure, we can generate those intermediate predictions, and we will save the predictions once we believe we have reached the stable prediction. Since usually for online learning, there is a burn-in data size, which means in the early stage the prediction is still messy and we cannot trust them. And if we have enough training data set, we can just set up a burn-in data set data size as B and start recording the prediction after B examples. And then we can go over, say, K iterations of stacking if we have enough training data. And this is under the assumption that I have enough data. I only need to go over the training set single pass, since the base learner is a single pass online learning algorithm. So even in, say, the case level of stacking, we need to keep this K plus 1 times B examples. And we don't need to maintain many classifiers in our system. Usually, K classifiers is enough. And this is very useful if we have data streaming by. And this online version of stacked graphical model can be applied to streaming data as well. But in reality, we cannot assume there is always enough training data set, so this is a practical solution. We will hold half of the data set, and say after half of the examples have passed by, we start recording the predictions from the base online learner. Then we learn another model from the second half, and we apply this model to, say, the first half, so that we have the predictions for oral training examples. So this procedure is actually one pass and another half pass over the whole training data set. So I would say this is the real case. It's not single pass over the whole training set. In practice, it's one pass and half pass over the training data. Again, I evaluate the online stacked graphical model with document classifications and name extraction here. And the dataset and the relational templates are discussed before. So I would just talk about the baseline models here. Here we compare to two baseline models. Since in the standard stacked graphical models, we use maxent as a local model. And in this online version, we can use a modified balanced window as our base learner. And we also compare to relational dependence networks just to show the accuracy is competitive. And the stacked graphical models here, we consider both standard stacked graphical models, that is a stacked graphical model with cross-validation procedure to generate predictions. And we consider the online version, which is bounded with balanced window algorithm. And this table here shows the accuracy on the document classification. And we can see compared to the two local models, the balanced and modified window is a nice online learning algorithm. It's very competitive to the max-end model. And if we compare the standard stacked graphical models with two choices of base learners, they increase the performance of local models correspondingly. And if we compare this online stacked graphical model, which was built with the online scheme bounded with modified balanced window learning algorithms, we can see the performance, the accuracy is still very competitive, either compared to standard stacking or compared to state-of-art relational models. And this is the result on the name extraction. And the competitive relational model here is conditional random fields for name extraction. And again, I compare those CRF models to standard stacked models with different local models and also the online version. And it's very interesting, the gain of performance compared to CRFs was primarily from the flexibility of choosing a relational template. Since if we can recall the relational template here, that's a relational template with dependency both among the adjacent words and the same words. So if we compare to this, I won't conclude that CRFs are not great models. It's just our model here can capture long-range dependencies. It's a pity I didn't get a chance to compare to a skip chain CRF models, since Andrew McCollum did report a gain of skip chain CRF compared to standard CRF. So yeah, I have to admit here the competitive models are not strong enough, maybe. But that's not the key point here. The great thing about this online stacked graphical models is the big success in the sense of training time required to get this model. Say, compared to standard stacked graphical models, that is a model with max-end base learner and cross-validation procedure to get predictions. In average, the speed up is nearly 60. And yeah, I can. You might argue that that's because you compare to a slow max-end learner, not just from the cross-validation procedure. It's also the competition between max-end and balanced window. And here I also compare this to a relational model with something based on the voltage perceptron. So here I would say the local model is more efficient. And even compared to those efficient local models with relational learning setup, the online stack graphical model is still a big success. All right. So now we can sort of claim a more complete story about stacked graphical learning. It can capture the dependency among the datasets and provide accurate performance, and also it obtains the efficiency in both training and inference. So I think I will spend like 5 minutes on this KDD cup project. The problem here is we are given the Netflix training dataset, which contains about 18,000 users and 18,000 movies and 500,000 users. The ratings are over 100 million. And in addition to the original Netflix training dataset, we can collect some movie information from the internet. So that's all our information sources. And the test set is 100,000 pairs of users and movies. We need to predict the probability of their review in the year of 2006 for this pair. And within this task, there are many challenges, and especially when we consider this as a classification problem to answer the question like whether it's a positive, which means there is a rating, or it's a negative, means there's no rating. Then under this setup, we have huge amount of data, since where it considers all the possible pairs of user and movies, many millions of examples. And if we consider the information we can collect, there is information from the graph if we view the user and movie as nodes and connect them by the ratings. And also there is features from, say, the movie database. We can describe the movie by the directors, by the actors, by the stories. And in solving this problem, we need a learning algorithm that is both accurate and robust, since when we started the dataset, we did observe a lot of noise in the dataset. So finally, we proposed two strategies to solve the challenges within this problem. One is a downsampling scheme, which will generate a reasonable sized training dataset for our learning algorithms. The sampling scheme here is we pick up a movie according to the frequent that movie has been reviewed, and also picking up a user according to the probability that user reviewed how many movies. And we removed the pair of user and movie if it's already in the training set. So it's sort of a rejection sampling strategy. And it turns out this sampling scheme does capture the distribution in the dataset. Here the blue is the positive rate in the testing example. And we can obtain this after they release the answer for the test set. And this is a positive rate in our 6 samples. And below here is the positive rate within the whole Netflix training set. And we can see if we, say, do a random subsampling, we might end up here, and the distribution is so different. But with our rejection sampling strategy, we sort of capture the correct priors. And to combine the information for multiple resources, we kind of use the ensemble strategy. But first, this is the features from multiple domains. We can calculate features based on this graph topology, and we can calculate features by representing a movie with vector, say, in the bag of words representation. Then finally, we will have a profile for the movie, which contains the information from the graph topology from the movie content. And we have a profile for each user. And for each user, we kind of model the user's preference by the movies having been reviewed by this user. For example, given a pair of movie and user, we can generate the final feature vector we use by checking this movie to the list of movies having been reviewed by that user. And finally, we record the similarity scores and the count of match. And our learning scheme is finally, we choose this ensemble classifier by combining sub-classifier trained through sub-feature spaces. And this is the solution we submitted. And at earliest stage, we did explore those single classifiers like max end, ridge correction, SVM, and we tried some averaging models by simply combining those sub-classifiers trained with sub-feature spaces with equal weights. And it turns out learning the weights is a good strategy. So I would say, oops, let's stay here for one more moment. The solution we submitted is still in early stages, still a quite naive solution. The benefit I gain from this project is more about some hands-on experience of working with real problems, and I really had a lot of fun working with it, and it helped me to realize that my interest is in working with real problems and trying to look at the issues of, say, dealing with huge data set when developing a learning system. We need to balance between the accuracy, the efficiency, and the generalization ability of the learning algorithms. And also, there's one interesting problem of how to combine the features from multiple domains, since where we look at features from abstract graph and also from some text descriptions. It's a very challenging problem to capture the nature of the user's preference. We explored the model by, say, building a model within each sub-feature space, but that's just one way. Maybe we can develop more advanced models to solve this problem of combining features from multi-views. That's what I'm interested in doing in the future, and I think that's it.
So one question I had is, in some of this work when you're doing the text classification stuff, you're comparing graphical model methods to graphical methods. Did you look at non-graphical models? I mean, why should we even be doing graphical modeling?
Yeah, that's a good question. I think, in general, I would say graphical models is not necessary, since I did compare to a model based on boosted decision tree, but with well-tuned relational features. And here the result I showed is with different models, but the kind of the same bag of words features for them. And in my thesis, there is a case study where I tuned the features very well, and the boosted decision tree can achieve a very nice accuracy. But if, say, we give the universal feature as input, graphical models applied to this relational classification problem usually give better accuracy.
Is it possible to prove that the ceiling graphical model is really the ceiling? I mean, it seems sort of intuitive, but
right.
I wonder if there's a proof.
Yeah, very good point. I didn't do that, but I think if we look at the idealized version, we might be able to prove that, since in the idealized version we kind of sample from the distribution obtained in the previous stage. If it's the case of the ceiling model, then that means we sample from the true distribution. Yeah, I think it's hard to conclude at this moment, but I can definitely look into that by replacing that sampling from previous stage with sampling from the true distribution.
So the theoretical convergence insight that you alluded to kind of troubles me a little, but it seems like you can't prove convergence without making some ergodic-like assumptions on the graph itself.
Oh, right. That is like something I didn't include here. So the general assumption would be quite similar to what's happening in the Gibbs sampling.
So so then you don't have to make certain assumptions on how the graph is partitioned, and certain assumptions on how
right.
the cross-validation strategy is set up. And even then, it seems like you can easily set yourself up to cycles because of the way. Is that right? I mean, you're essentially, at least it looked like the insight essentially smooths out certain periodicities that might actually occur in the algorithm.
So if we look at the graph over the relational dataset is like a very massive graphical model. So there is no longer graph partitioning concerns in that graph. But if we move from idealized version to our practical solution, there is the concern of designing a nice relational template that can capture enough information from the Markov blanket. But if we look at the idealized version, this problem doesn't exist. Okay, thank you.